All right, so I'm going to try to give a fairly brief lecture today to leave some time for lab. Fortunately, what we're covering today is, I would say, fairly straightforward relative to some of the things we've done already, because we're just extending the hypothesis testing that you've been learning to two sample means. So the same distributions, the t distribution and the z distribution, but just introducing their application to the so-called independent and paired two-sample tests. And we'll go ahead with both hypothesis tests and confidence intervals for these paired and unpaired two-sample tests. So just as a quick review from the last class, I introduced hypothesis testing, first using the z distribution, and we use this when the standard deviation is known. It's not estimated from the sample, or where the sample size is so large, like greater than 500, that it makes very little difference. And from this, you've learned both how to construct a confidence interval, which is just a sample mean plus or minus the so-called margin of error. The margin of error involves the standard error and a critical test statistic, which in this case is calculated from the z distribution. And alternatively, for our hypothesis test, and there's an equivalence between them, you calculate a test statistic from your sample mean minus the hypothesized mean based on your null hypothesis divided by the standard error. And then if you're doing a hypothesis test, you compare that value of z to the critical value, or you calculate a p-value based on this test statistic. And using the t distribution, it's exactly the same thing, except we use the value of the t statistic, or the probability based on the t statistic, looked up in a t table, which has not only this alpha over 2, but it has a degrees of freedom. For a one sample test was just your sample size minus 1. Sounds like it's working, Tony? Great. So moving on to two-sample hypothesis testing, this is a pretty common practical situation where instead of having in advance a hypothesis, a null hypothesis that is based on the population, our null hypothesis has to do with two samples, not comparison to a population. But fortunately, the tests that we've just covered there can be learned without too much modification and applied to the two samples. Most important thing to recognize when doing this is whether these are paired samples or independent samples. And essentially, paired samples are ones where you have two measurements on the same subject. So either 2 points in time, left and right eye, things like this, or two twins, but something where there's a natural pairing between the observations. Whereas independent samples, these are really just one measurement per subject. So those are two completely independent samples.
Can you give an example?
Yeah, I'm going to give you a few examples. So some examples of unpaired measurements. These could be, let's say, the birth weights of unrelated boys and girls. If you were comparing you had a hypothesis, your null hypothesis is that birth weights are the same for boys and girls, and you look at independent samples. Laboratory tests from two different participants in a clinical trial, those are independent samples because they're different participants. Or a comparison of household health care costs in the US and Canada, those are going to have to be independent samples because they're different households in the US and in Canada. So what all of these have in common is that these are two really independent sets of measurements. A few examples of paired or dependent measurements. One could be the difference in birth weights of twins. So if in that example of the birth rates of infant boys and girls, if we had instead looked at pairs of non-identical twins where where one was a boy and one was the girl, and we wanted to test a hypothesis about their birth weight being the same, that would be a paired test because those twins come in pairs. If we had pre and post laboratory results for each participant in a clinical trial, that would be a paired measurement because it's 2 measurements on each participant. Ocular measurements on the left and right eyes of the same subject, because it's 1 subject, 2 observations. Stress measure scores in twins or husband-wife pairs. So in these cases, they're different people, but they're not independent because they're grouped together by twins or being in the same household. Or finally, measurements from 2 methods of conducting an assay on a patient sample. So you have the same sample, but 2 different measurements on that sample. Like say you're comparing 2 different ways of measuring hemoglobin levels, and you want to know if you're getting the same results from those 2 measurements. Those would be paired samples. Any questions so far?
Yeah.
Yes. Yes.
I have a question. What's the difference between the second one, this pre-post laboratory results for each participant in a clinical study, and then the past slide, there was laboratory results for 2 different participants in a clinical trial?
The key thing was that these are different participants, so those are like independent.
And then over there it's the same person.
Over
and
here, this is
and
right.
Just the before and after. Okay, got it.
Right, the same person before and after.
Okay.
Yeah.
So with the husband-wife pairs, you said they're dependent because they're in the same household.
Mm-hmm. Right, because rather than doing, like if you were testing a hypothesis that was a comparison between married men and married women, but not the ones who are married to each other, those would be independent samples. Whereas if you're looking at those married pairs, then that becomes dependent samples. The key thing is that there is a pairing. You're like if you were looking at the independent samples, it doesn't really work. But those could be 2 independent samples, but if there is a link between them, then they're paired or dependent samples. All right, so to make sure you have it, I'm going to ask you some questions. Which of these are paired measurements? So a comparison of the average heights of males and females. No, that's not paired measurements, not as stated here. To compare anxiety levels of individuals before and after an intervention.
Yes.
Yeah, as long as you're looking at, at individuals with a measurement before and after the intervention. Comparison of anxiety levels of 2 groups, one with and one without the intervention.
No.
No, very good. And just to drive this home, if there is a natural pairing of the measurements, then you must use a paired test. If you are not using a paired test, you're making your violation of independent samples is violated because they are not independent samples. I'm going to talk about the paired test first because it is really similar to the 1 sample tests. So with the 1 sample test, we calculated a z statistic like this. With paired samples, the z statistic is exactly the same, except that I'm using a d to represent the differences, and a delta 0 to represent the population difference under the null hypothesis. So whereas we're looking at individual measurements in the single sample test, we are looking at individual differences in the corresponding paired test. Now, I'll give you an example of how this works. But essentially, all it involves is calculating the differences for each pair, just subtracting them and then doing a one sample test. That's all. And it's the same thing with the t-tests, just applying the same test, but on the differences. So the mean of the differences, and also the standard deviation of the differences here. So here's an example, the cell phone study, a hypothetical study where the question was, does cell phone use while driving impair reaction times? That is tested by an experiment where the volunteers use a machine that simulates driving situations, and at various periods in the simulation, they are flashed a red or a green light and told to press a brake button as soon as they detect a red light. And in this study, for each subject, the experiment analyzes their mean response time, both for 32 students randomly assigned to the cell phone group and 32 to the control group. So in fact, is this a paired or an unpaired design? This is unpaired. This is not paired. These are 64 individuals, 32 assigned to each group. So looking at some exploratory data analysis of this hypothetical study, we have the two groups, the cell phone group with a mean response time of 585 milliseconds, and the control group with a mean response time of 533. And then we have a far outlier out here. So to analyze this, we're going to need a t-statistic for two independent samples. And I'll walk you through this first. And this is the slightly more complicated test. So we have two different groups. Each one of them has a population mean. Our null hypothesis is going to be that those two population means are identical. And so in this case, because they are independent samples, we're analyzing the difference in the means of those two samples. If they were paired, it could be differences in individuals, but this is not the paired test. The z-score here, that this calculation is essentially the same as it is for one sample, but everywhere that we have something in the one sample, we're just substituting a difference. So a difference in the sample means, difference in the population means, and something else for the standard error here, but it's the standard error on this difference in means. And there are ways to estimate this, standard error for the two independent samples. Sorry, this is, this is for two independent samples where we have the population standard deviations. And this is essentially a weighted average of the standard errors. When doing a two-sample t-test, you have to make a choice between whether or not you're going to pool the standard deviations that you're estimating from each group. If you do not pool it, again, this numerator looks the same as it did for the one-sample t-test, except that it is with differences in the sample means and the population means. And the denominator just has this slightly different, instead of just the standard deviation over square root n, it has this sort of average of those two sampled standard deviations. So this is in fact using both standard deviations, not pooling. It is also possible to do it with pooling, and in this case, the denominator has this pooled standard deviation. So instead of having an S1 squared over, or S2 squared over N2 and an S1 squared over N1, it just has this pooled standard deviation, and there's a formula for calculating it. I'll tell you a little bit about making that decision between the pooled or the not pooled standard deviation. Essentially, when you pool the standard deviations, you're making the assumption that that standard deviation is the same in the two populations. And the test will be more powerful if that assumption is true. But if it's not true, you can run into problems with your with increasing your type 1 error rate. So if you're not sure, not pooling can be a safer assumption. There are risks in not pooling as well. So as a rule of thumb, don't pool if the two standard deviations are very different, like say by more than a factor of 2. But as another rule of thumb, you probably should pool if you have one very small group. So if N1 is 4, so you have one group of 4 and then another group of 20, you don't really have enough observations in one of your groups to accurately estimate the standard deviation. So if you have very unbalanced groups in one very small group, you probably need to pool your standard deviations. That is assuming that it is reasonable to do so. If you know in advance that this is a violation, that in the population the standard deviations must be different, then you don't pool because you know you're violating an assumption by pooling. The degrees of freedom, it's much simpler. If you're pooling, it's just your total sample size minus 2. If they're not pooled, this is a so-called Welch's t-test, and it has a non-integer degree of freedom, which is approximately the minimum of your two sample sizes minus 1. It'll be a little bit smaller than that, so that your p-value that you estimate this way will be a little bit bigger than the true p-value, and your confidence interval will be a little bigger. So it's a conservative estimate. But if you're using software, it will tell you it will calculate this formula and give you your non-integer degrees of freedom if you're using the Welch's unpooled standard deviation t-test. So just as an example, going through this, one, I haven't shown the data, but you saw the box plot. It kind of looked like there was a difference. If for that data set you calculate your t-statistic, you get something sort of marginally significant, p-value of 0.011. But it's enough to reject the null hypothesis that the mean response times are identical. So we conclude that the mean response time is different between the cell phone group and the control group, and we observe that response time is greater in the cell phone users group. let's consider if the study had been done differently using a paired analysis. So instead of these two independent groups, suppose that we only had 32 volunteers, and instead we made them do the driving test 2 times. One time when the reaction times are measured without the cell phone, and then again with the cell phone. So it's a paired design because we have the same individuals doing the test under these 2 different conditions. So in this case, for each measurement, you have these 2 observations, one for not using the cell phone and one for using it. And then we calculate the difference in response times for each one of those individuals. And then we're going to do a 1-sample test on those differences. So going through those procedures, again, we have now a much larger T, smaller number of degrees of freedom, but this turns out to be highly significant. I can't quite read it up here, but for 95% with, let's say, 30 degrees of freedom, the critical value, sorry, for T.025, the critical value is only about 2. So we're definitely going to reject the null hypothesis. If we use this table to calculate a 95% confidence interval, it does not include 0. So our confidence interval around the increase in mean response time when using a cell phone is between 32 and 70 milliseconds. And if we were to plot this, it would just look like a single box plot of the differences. And one thing, just as an example here, the reason for doing this paired test is that it's efficient. So we're able to get probably better power to test this hypothesis using half as many participants, because there's a certain natural variability in response time among participants, but that is controlled for in this paired design because we only compare participants before and after. So if there's an individual who's an outlier in just because they're very slow in their response time or very fast, they may not be an outlier in their change in response times. So it's an efficient design. Yeah, there's a little bit of skew to the right here, not very much. It's not enough that I would worry about it for a t-test. So for the confidence intervals, as usual, you can check whether the 0 falls in your confidence interval and use this for as an equivalent to your hypothesis test. But the key thing I want to highlight here is that you construct a single confidence interval, even for whether it's paired dependent samples or 2 independent samples. We construct a single confidence interval on that difference in the means. We're not constructing 2 confidence intervals, one for each mean, at least not for comparing those groups. So not a separate confidence interval for each sample. That's a kind of common misconception among introductory biostatistics students. You learn how to calculate a confidence interval for 1 sample, and when you get 2 samples, you go and calculate 2 confidence intervals and say, oh, they overlap, so there must not be a significant difference between these groups. That's not true. You can have cases where there's overlap between those 2 confidence intervals, as I've plotted here. You can have a case where your confidence interval on the difference does not include, let's say this is 0, but there is still overlap between the individual confidence intervals. So you have to do it this way with a single confidence interval if you want to do some kind of inference based on that confidence interval. Does that make sense? That's an important point. So just to summarize these two sample procedures, for paired samples with continuous data, you take the difference and then use the one sampled T or Z methods as before. For independent samples, you instead use differences in means, not between observations, either differences in means or differences in proportions, and then use these slightly modified T or Z distributions. Or if it's proportions and they're large enough sample size, use a one sample Z test. So the assumptions involved here for unpaired, it's that you have two independent samples. For paired, that these pairs are a unit, but the units are independent. So like in the example of the driving test, that these tests are done independently for each individual, and those individuals can each be considered an independent observation. These all assume that the population values are normally distributed and that our samples are obtained by a random sample. I'm going to end off with a little bit of just discussion of these limitations and how to and not to interpret significance tests. So a first limitation that I want to highlight is that statistical significance does not necessarily equal practical significance. And this is especially important to keep in mind either when you have very small sample sizes, because then even a large deviation from your null hypothesis, you're not going to have power to detect. So, so it tells you very little, like a statistically insignificant result does not tell you much. And on the other hand, if you have a very large sample size, then even really tiny deviations from that, from the null hypothesis being true, can give you highly statistically significant results. This is an example of the effective minimum bid on eBay camera sales price, where there were 341,000 auctions here. And this was a paper on the pitfalls of very large sample sizes, where they are actually using the logarithm of the minimum bid and found this coefficient of 0.1, which has a p-value of essentially 0 and a 95% confidence interval of 0.099 to 0.103, so a very small confidence interval. But so the null hypothesis is rejected, but put into the language of this particular study, a 1% increase in the minimum bid is associated with an average of 0.09% increase in the final price. So whether or not that is important is a separate question from whether it is statistically significant. It's clearly not a big difference. I've mentioned this to you before, but I want to emphasize it again. The p-value is not a probability of the null hypothesis being true. Or another way of saying this, no evidence of a difference is not the same thing of evidence of there being no difference. So if you get a p-value of 0.01, that does not mean there's only a 1% chance of the null hypothesis being true, or a p-value of 0.9. A p-value of 0.01, that means that if the null hypothesis is true, there's only a 1% chance that you would observe a sample as extreme or more extreme as the one that you observed. Or in other words, it's a probability of your type 1 error of rejecting the null hypothesis when the null hypothesis is true. On the other hand, you can estimate your evidence for the null hypothesis. That is the power, which we'll get to after the exam, or at least for calculations of power. Just as an example of how this is reported, researchers didn't find evidence of the effectiveness of a treatment on self-reported pain, p equals 0.2, p-value of 0.2. Does this mean that there's an 80% chance that the pain reliever has no effect?
Okay.
Is anyone feeling tempted to say yes? Now, this means that if the pain reliever has no effect, there's a 20% chance of us rejecting that null hypothesis. There's an 80% chance of us, or there's a 20% chance of observing a sample as extreme as we observed. An 80% chance that this sample is consistent with that null hypothesis.
So you're saying that you can't say that?
It's not evidence for there being no effect. No, all we can say is if there is no effect, our probability of observing this is still 20%, even if there's no effect of observing the difference that we observed. So alpha equals 0.05 is super common. It's the most common threshold, but it is important to remember that it is an arbitrary cutoff, and there's no real border between significant and not significant. And one case you can see this come up is studies that have multiple endpoints. So where those endpoints are fairly correlated to each other, you can see one where one has a p-value of 0.055 and the other one is 0.04. So should this be interpreted as strong evidence for one endpoint and no evidence for the other endpoint? Like if this is, for effectiveness of an intervention on two different measures of the same outcome. Say we're talking about viral load suppression of HIV patients and CD4 count being high. So those are related endpoints, but not the same. If we found these two different p-values, does that mean that the intervention is effective for suppressing viral load, but not effective for maintaining CD4 count, the red blood cell count? No, it's not evidence of that. In fact, these are pretty close p-values. It's kind of on the threshold for both of them. I would say it's reasonable evidence for both of them that there's some relationship between the intervention and these two outcomes. Yeah.
If there was a large difference, would you say something different?
Yeah, if there's a large difference, I would be more inclined to say maybe there really is an association or a true alternative hypothesis for one of them and not the other. There's a large difference.
I wanted to say no, but I didn't know why.
Right. Yeah, I'm saying that because these p-values are quite similar. This is a kind of common misinterpretation is to forget that significance tests are about the central tendency of the population, whether it's a mean or proportion, and not about individuals, especially when it comes to confidence intervals or hypothesis tests. So for example, researchers measure serum lead levels in a random sample of 100 children from an area with potential lead contamination and find a mean serum level of 5, which is lower than the normal limit of 10. So, so they actually found a lower than what is allowed, and they reject this null hypothesis. Does this mean, so with a p-value less than 0.01, so this is a one-sampled test looking at the blood serum levels of lead and finding that that mean in this sample, or in the population from which the sample is taken, is less than this this regulated limit. So does that mean that fewer than 1% of children have serum levels exceeding the limit? No, it doesn't. All it means is that if the mean serum level of this population is 10 micrograms per deciliter, there's a less than 1% chance of us observing a mean of less than 5 or greater than 15. That's all that means. So it's unlikely that the true mean serum level in this sample is equal to 10 micrograms per deciliter. Probably less. All right, finally, assuming that n is small, or if you assume that just because n is small, you can't believe in the results of a significance test, or conversely, if you have a large sample size, then the results must be true. That's a misconception, because the statistical test accounts for sample size. So as long as your assumptions are met about the distribution, about the sampling that was done, if you have a true, correct random sample, then these probabilities are correct, and they account for the sample size. They account for the fact that with a smaller sample size, you expect more variability. With a larger sample size, you get less sampling variability. What they don't account for are things like selection bias and measurement bias. And even if you don't have any of these misconceptions, it is appropriate to have some skepticism in interpreting significance tests. One a good skepticism to have is with the study design, because no statistical analysis can remedy flaws that were present in producing the data, such as can come from voluntary response sample, uncontrolled measurements, or measurement bias. And this has come up in cancer research. This was a big story back when I was a postdoc in cancer research. There were a set of genomic studies that said that you could predict response to therapy for a couple of different cancer types just based on the tumor genomes. And then all of that fell apart. It was on the front page of the New York Times after a couple of statisticians reanalyzed the data and couldn't reproduce the results, or found that it was due to technical measurement bias. Since tests can be statistically significant by chance, there is always a risk that the type 1 error rate that you read is somewhat inflated because you're not seeing the results that were not significant. For example, in this XKCD cartoon, they have testing whether 20 different flavors of jelly beans are linked to acne, and in one of them there's a p-value of less than 0.05, and then that appears on the front page of the news. Kind of extreme example, but this does happen. Different people perform the same kind of tests, and only those that get a significant p-value end up getting published. And a related thing to that is that the true effects are often not as large as the initial estimates, and that can also arise from publication bias. And this occurred in a very famous case of the antidepressant reboxetine, which passed a clinical trial and was estimated to be very effective for treatment of depression. But then in subsequent attempts to replicate the study, it was found to be less effective and more harmful than originally reported. And it was decided this was probably due to publication bias in the initial trials. And it was from this that now anytime you are performing a clinical trial with the purpose of having a drug approved, you have to pre-register that trial, or else that the results of that trial will not be considered in whether to approve the drug. When it comes to other kinds of clinical trials where there is not the FDA involved, there is not necessarily such a rule. It's up to the journal whether or not they require pre-registration. So something to be aware of. And with that, I'm going to quit, and Tony will have about an hour to do. So let's take 5 minutes, and we'll start up again at 7 o'clock.